Here we're going to tackle contiguous array, which we're going to try and solve with minimum complexities of O(n) time and O(n) space. In our problem statement, we're given a binary array nums, and we want to find the maximum length of a contiguous subarray containing an equal number of zeros and ones. If we take a look, we've got four methods. They are A, stack, B, Kadane's algorithm, C, two linear scans, or D, sliding window plus hash table. I'm going to give you a few seconds while you select the best method to solve the problem. So for those of you who recognize the most optimal solution, congratulations. And for those of you who just want to see the code, the answer here is D, sliding window plus hash table. The brute force approach to this is rather simplistic. It would involve using nested loops and counting the number of zeros and ones within each subarray. If we count an equal number, then we can update the maximum length of contiguous subarray found so far. However, using nested loops in this way would probably yield a time complexity of O(n) squared in the best instance, and is suboptimal for this problem. Let's take a look at a more optimized solution, which involves using a cumulative sum. So we're using a sliding window along with a hash table to efficiently find the maximum length of contiguous subarray. By maintaining a cumulative sum of the elements in the array, that is, decrementing when we find the binary value 0 and incrementing the cumulative sum when we find a 1, along with storing the first occurrence of each cumulative sum in our hash table, we can determine the maximum length of the contiguous subarray containing that equal number of zeros and ones. Obviously that's quite a wordy explanation. I'm going to go through this line by line to ensure there's full understanding. So we start with this CumSum variable, which is initialized to 0, as well as this hash table, myMap. This is used to store the first occurrence of each cumulative sum, and it begins with this key 0 and value -1. This is a dummy entry in our hash table, and we'll use it to handle cases when the cumulative sum becomes 0 again in the future. After we've done that, we've got our variables sz and result. Obviously, the size of the array, and this will eventually be the result we return. After that, we're going to iterate over each element in nums, using this for loop. For each element, we're going to check if it's 0 or 1. If we find a 0, then we decrement cumulative sum or CumSum by 1. Conversely, if it's 1, we increment our cumulative sum by 1. We then check if the cumulative sum, CumSum, exists in the hash table myMap. If it doesn't exist, we store the current index I as the value for the cumulative sum in the hash table. If that cumulative sum already exists in the hash table, we calculate the length of the subarray by subtracting the index stored in the hash table from the current index, that is, I minus myMap CumSum, as shown here. We update our result variable with the maximum length obtained so far using the max function. Finally, we return the maximum length of the contiguous subarray after we've gone through the whole nums array. So, hopefully you can understand how this solution leverages the sliding window technique and use of a hash table to efficiently find the maximum length of the contiguous subarray. Now, that's one more problem solving session solved using this Coding Card Sharp app. To really check everything, I'm going to show you the problem and possible answers one more time. So, to solve the contiguous array problem, the best method from among these four is sliding window plus hash table. There's a short explanation as to why, and in our application we also provide explanations as to why these other three are suboptimal. But you'll have to download it and find the web app in our description to do so. We do provide solutions in C++, Python, and Java for those people who prefer the more popular languages. If you're still struggling with this problem, I'll finish this video by recommending you check out the Udemy course in this description. Dr. Ibrahim offers a more visual explanation than the one that I'm providing you. Thanks very much for watching, and I hope that this has helped you with this problem.